I would just like to thank the organisers for letting me out of my box at the University of Sydney to come here and talk about computational chemistry and also a bit of quantum chemistry too. So I mean I've tried to keep the chemistry general. So basically maybe all you need to know is that matter is made of atoms. Atoms bond together to form molecules, and that electrons are involved in some way. So just briefly, I'm not going to be these pictures here. I'm not going to be talking about them in this talk, but I just thought, but they're from my simulations, and they're just three hydrogen molecules bound to this lithium benzene system. They're simulated at a temperature of absolute zero. So it's the quantum mechanical ground state. And so what quantum mechanics tells us is that the hydrogen molecules actually spread out around the top of the lithium benzene system, forming this sort of donut. So that's the sort of weird things that quantum mechanics does, and I'll come back to that later. But first, so I'm going to talk about how we can do chemistry with computers. We're going to then look at sort of machine learning and how neural networks can help us calculate the potential energy surface, and we're going to look at learning how to make accurate chemical predictions. So first, how do we do a chemistry with computers, or how many cheesy sort of computer chemistry related pictures can I sort of use in this section? So let's find out. Okay, so computers. So computers can help us investigate chemical systems at the atomic and the molecular level. They can provide a level of detail that you just can't get by performing experiments. So in most cases we can actually see what is actually going on in our chemical system, sort of atom by atom, and you just can't get that in experiments. So computational chemistry can give insights into how atoms bond together, the overall shape of a molecule and its spectroscopic signature. So how it reacts to when you shoot lasers at it, basically. We can also calculate energetics of a particular chemical reaction that we're interested in to predict a reaction pathway. And we can also predict properties of new materials without even going into the labs to make it. We can do it all just on the computer. So if we want to do computational chemistry, we first must start with some sort of theoretical groundwork. And I thought I'd show this just with a photo of the great theoretical physicist Paul Dirac standing in front of some theory. And you might look at that and say, oh well, that's the anti-bonding orbital of a hydrogen molecule. But I actually think he's just drawn a pair of breasts on the board, and look at him there. He's trying not to suddenly burst out laughing. So when we have our theory, then we need to come up with some sort of our algorithm so we can run a simulation. So in computational chemistry, we're all still using Fortran. Fortran is still probably the best language to use when you just need to do some sort of hard, heavy number crunching. So we also need a big computer. This is the NCI National Supercomputer down in Canberra. It has about 53,000-ish cores, probably about the same size as your average Hadoop cluster these days. So then we run our simulations, and this is one of mine. So once again, we can actually see what what the atoms in our simulation are doing. So this is simulating molecular hydrogen interacting with a type of hydrogen storage material. So this is actually, so we can see many sort of thousands of hydrogens, but these are actually all just random walkers in a Monte Carlo simulation, and then we average the results to get our chemical behavior. And after after we've finished our simulations, we've done some science. Okay, so if I haven't convinced you yet of why we want to do computational chemistry as opposed to experiments, I found this horrible poem that someone wrote back in 1983 about sort of theoretical versus experimental chemistry. I'll just read you the last stanza. It's terrible and it brings me great joy to share it with you. So theory guys have got it made in rooms free of pollution. Instead of problems with the reflux, they have only solutions. And when the feds announce a list of carcinogenic terrors, the theorists sit safely at their terminals, fixing errors. In other words, experimentalists will likely die of cancer from working hard yet fruitlessly, till theory gives the answer. So, thank you. So we can blame this guy here for that abomination, but we do theoretical chemistry. So one, we don't need to worry about sort of breathing solvents day in, day out in the lab, and if we just compute hard enough, we will eventually get the right answer. Okay, so I'm going to present some machine learning methods now as used in computational chemistry, but I just want to give a brief disclaimer. So in the work that I've done so far, I haven't done anything sort of special. I just run a bunch of simulations and then just average all of the results. And so I'm actually quite new to the field of machine learning, but I thought, but looking around computational chemistry, I see that lots of groups are starting to use it, so I thought I'd come here and present some of it to you. So, but I just want to note that I haven't used any of these methods myself, so if you have a sort of in-depth question, I may not be able to answer it. Anyway, okay, so neural networks and potential energy surfaces. So, first, the molecular potential energy surface describes the potential energy of a molecular system, and it describes how it changes with the shape of the molecule. So if we take water here, H2O, we can describe the shape of water in terms of the bond length between the oxygen and hydrogen 1, and the bond length between the oxygen hydrogen 2, and the angle between the hydrogen, oxygen, and the hydrogen. So the potential energy surface will be a function of those three geometric parameters, and so in general, the potential energy surface of a molecule is a landscape characterized by high peaks, deep valleys, and a sudden change. So all the chemistry occurs on this potential energy surface. So I'll show one just for the hydrogen molecule, because it's a one-dimensional surface as a function of the distance between both of the hydrogen atoms. So it looks a bit like this. So, but what it says, so at long separations, the potential energy stays constant. So it doesn't matter how far we stretch the hydrogen atoms, the potential energy doesn't change because there's no interaction between them. But bring them closer and closer together, you eventually form a bond. So a bond lowers the potential energy of both of those, but then force them too close together. The repulsion between the nuclei takes over, and the energy shoots up really quickly. Of course, if you really force them together, eventually you would have nuclear fusion, but that's outside of the realm of the realm of chemistry. So, okay, so in general, the molecular potential energy surface is a complicated function with 3n-6 dimensions, and the vast majority of the time we can't actually write down, like we can't write it down mathematically. So, but we need an accurate potential if we want to simulate the dynamics of a chemical system. So So we can perform a sort of quantum chemical calculation, but I'll come back to how we do those a bit later. But so if we perform a quantum chemical calculation, we get the potential energy, but quantum chemical calculations can be expensive. They can take time. They can take anything from a few seconds to a week or a month. So, and when in a simulation, when you need on the order of hundreds of millions of potential energy calculations, you just can't calculate it directly. So we need to do something else. We also can't just, knowing that, we can't just grid a surface over all the degrees of freedom, because even with just 5 points per degree of freedom for the ethanol molecule, so 9 atoms, you'll need 5 to the power of 3 times 9 minus 6, well, almost sort of 500 trillion grid points for a 9 atom molecule. So dimensionality kills us. So, but can we use neural networks to fit a surface for us? So in their more simpler form, I know quite a few of you here sort of use neural networks for sort of deep learning purposes. But in their simpler form, they are sort of universal function approximators. So we don't know the form of the potential, but we can train the neural network with some data points and fit one for us. And that's exactly what they've been doing. So the first neural network was employed in 1985 to describe the interaction of molecular hydrogen with a silicon surface. So they used 750 training examples, and they noted that training takes about 30 minutes using MATLAB on a Sun Spark Station 2, which is, I looked it up, which is that machine there. They use the 80 megahertz CPU upgrade on that, but still, I don't think that's bad. You set it up to train, walk away, get a coffee, have some lunch, come back, and you have your potential energy surface. So with this first one, the accuracy wasn't that great, as you can see. I mean, there's so this is oops. So this just shows the error in the surface over there, over some data points, and as you can see, well, we want it to cluster around 0, which some of them do, but you also have some great outliers there. So it wasn't great, but this was 1995, and just having that potential energy surface, I think, is a great step forward. So since then, they've been used for many things. They've been used for water, hydrogen fluoride, silicon dioxide, for bulk carbon. There's the diamond structure of carbon, sodium, and so on. So I'll just show you how a neural network potential energy surface can be created for water. So with the water molecule, we have those 3 degrees of freedom there, and then they are the inputs to our neural network surface. So our inputs connect to our hidden layer with n nodes, however many you want, and with the required weights and so on, and then those are all summed to give the potential energy function. So written down here, so the potential energy as a function of R1, R2, and theta is equal to a sum over those hidden layer nodes multiplied by some coefficient, and and using the a sigmoid activation function there. And so the network's trained using the it's just a fairly straightforward feed forward network, and you train it using the usual back propagation and adjust the weights. So just a few considerations when using neural networks to fit your potential energy surfaces. Well, so there's the usual questions of how many nodes you use and how many hidden layers. So more may not necessarily be better. It may increase the cost of your calculation without really giving you anything more. There's, of course, am I overfitting to the data set, and can I extrapolate using this, using our neural network, or can I only interpolate with it? So if we say had a neural network surface for the hydrogen molecule, if I stretch the hydrogens really far apart, does that potential energy stay flat, or does it go crazy? So something that you may not have to usually consider, but we do, is that our potential energy surface must possess the correct symmetry. So in the case of water, we stretch this bond here. That is the same as stretching that bond there. Both of those should have the same potential energy. So a number of methods have been proposed to overcome that requirement, and we also need just a higher density of training points, so training potential energies in the regions of the surface that we actually care about, the ones that are chemically interesting. So we're usually interested in the minima, where we might have a new bond formed, and also the transition state, so a saddle point on the potential energy surface where the molecule might be transforming from sort of one geometry into another. So we need to make sure we have a good density of data points. So there's have a neural network surface for methane. I'll just very quickly go through it. So it's expressed as a function of the atom, as an exponential function of the atom-atom distances there. So between carbon, hydrogen, and then between the two hydrogens, and so they formed a committee of 26 hidden layer neural networks. So not just one, they use 26. So they use 410 sigmoid nodes in the hidden layer, giving 5,333 parameters that needed to be adjusted. They then trained them all with about 100,764 methane potential energies. Of course, randomizing the 80% that were in the fitting group and the 20% that were in the validation. And they just averaged all of them because they reasoned that, okay, so there's going to be some random component of the fitting error. Sometimes it might be above the actual result. Sometimes it might be a bit low. So they thought, well, we just average them all together and just to average out that component. And so I'll just quickly show this. So this shows the energy of various sort of methane configurations. And so as here, I think it does quite good. So I know those look terrible, but that's up at a very, very high energy of 25,000 wave numbers, and you're only getting about a 50 wave number error there. So I think that's very good, and it's all sort of all clustered around zero for lower energy. So I think they've done quite well developing a potential energy surface for methane. So just to wrap up this part of the talk, so the potential energy surface is a complex multi-dimensional function that we can't actually express analytically. But given a good set of training energies, so calculated with the quantum chemical technique, we can simple feed forward neural networks can be used to learn the potential energy surface of a molecule. You can then use these potential energy surfaces to actually perform simulations on, to calculate various chemical properties. And we can now, and they are now reaching what is called a spectroscopic accuracy. So which is what we want. Okay, so moving on to something a little bit different, we can use machine learning techniques to make accurate chemical predictions. I've subtitled this "Turning a Camry into a Ferrari." I will explain what that means shortly. So, introduction to quantum chemistry. Here we go. So chemistry is determined mostly by electrons. So electrons are subatomic particles that show quantumly behavior. They do weird things. They can spread themselves out. They can tunnel through barriers and so on. So I've just shown this here. So this is the famous. I'm not sure if you can see that. This is the famous double slit experiments where you're shooting electrons through two slits. So with small numbers of electrons, they just hit hit the screen as normal, but and then you shoot more electrons and more electrons. But as you gather more and more electrons, you actually get this interference pattern happening here. So if an electron was just a particle, it should just be sort of a sort of uniform distribution. But you have these sort of electron waves cancelling each other out a little bit, and that still sort of does my head in. So this is sort of quantumly behaviour, I'm calling it, that we must account for, and we can account for it if we solve this equation, the Schrodinger equation. So basically, the Hamiltonian operator operates on the wave function to give us the energy of the wave function and the wave function back. I don't know why this equation gives us quantum mechanics. I don't think anybody knows why except Erwin Schrodinger, and he's dead. So, So the chief goal of quantum chemistry is to calculate the wave function psi of a given molecular system. I wish it was that easy. Okay, so methods in quantum chemistry, and I'm going to do this with a car analogy. Okay, so here we have our methods, and as we go along there, they go up in a computational expense. Here on our y-axis, we have our basis set. So you're probably familiar with the basis set that we use to describe vectors. Well, in quantum chemistry, our basis set is our collection of functions that we're going to use to describe the electron wave function. So you can have a small basis set, or you can have a really large basis set. So at the bottom rung here is a theory called Hartree-Fock Theory, and I'm not going to go into it, but we essentially treat the electrons independently. They don't sort of communicate with each other. So if we do a Hartree-Fock calculation with a minimal basis set, we just have this sort of children's toy play car thing. It's not useful for any real chemistry, but it's a sort of toy that you can just use to maybe learn about your calculations. If we use a medium-sized basis set, we have a sort of 1990s Toyota Camry. So reliable, will get you from A to B, and nothing else. If we use a huge basis set with the Hartree-Fock method, we still have a Camry. So it doesn't get any better when you increase the basis set size. The next rung up is a Playset perturbation theory. All that does is sort of add a correlation in there to the electron. So one electron does something, and then the other responds to it. And so with a reasonable basis set, that's a BMW 3 series. It's a nice good solid drive, much better than a Camry, but still it isn't going to set the world on fire. But it's a solid method. So then at the top end of the scale, you have methods called like coupled cluster, full configuration interaction, multi-configuration interaction, blah, 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 blah. They sometimes add them together, so you have full configuration interaction, coupled cluster with perturbative triples. Anyway, the names go on, but if you wield that properly with a good sized basis set, you have a Ferrari. Basically, it's the absolute gold standard of quantum chemistry. Also, when you do those calculations, like a Ferrari, we all kind of hate you because we're all slightly jealous of your big computational resources. But it will give you the gold standard result. But if you use one of these methods with a minimal basis set, you have a sort of wrecked Ferrari. It's worse than a useless, and everybody gets to laugh at you. Other methods that I'm not going to talk about are density functional theory and quantum Monte Carlo, but I'm not really going to go into those. So the problem here, I'll speed up a little. So if we want to make accurate prediction of thermochemical properties, such as the internal energy of a molecule, the rate at which it reacts with something else, it can be very computationally expensive. You're up on that around that Ferrari region of the of that plot before. But we can use, but in a lot of the cases, a cheap method that Hartree-Fock right at the bottom actually gets us 90% of the way there, just like the 1990s Toyota Camry will get us 90% of the way there. So the remaining 10%, which we're going to call delta, is the killer. That remaining 10% is a calculation that takes weeks, basically. So can we use machine learning to give us the extra delta? So can we take some property that we want to calculate? Can we express that in terms of the property calculated with the cheap theory plus some machine learning correction? And so this part is just from this paper. Big data meets quantum chemistry approximations, the delta machine learning approach. So basically, we say, can we train the machine learning method on the error between the inexpensive sort of base level of theory, so our Camry level of theory, and between that and the more accurate, sort of expensive Ferrari level of theory. So, or train the machine on the difference between a Camry and a Ferrari. More specifically, can we predict a given property at the Ferrari level using that property calculated at the Camry level plus the machine learning contribution? So it is our Ferrari property is approximately equal to our Camry property plus our machine learning contribution here. So this is a so they've used kernel ridge regression. Our D here is the calculated distance metric between the molecule that we want to know about and the molecules in our database, while sigma here is the kernel width, and the C is just our regression coefficients. So basically, I'll just show one example. So they took the training molecules, they took 1,000 with the overall formula C7H10O2, and I've just shown some examples. So that's a fairly big chemical space there. There are many ways that you can arrange 7 carbon molecules, 7 carbon atoms, 10 hydrogen atoms, and two oxygen atoms, and they took the property calculated at the Camry level and the Ferrari level, put it into the machine, so they're learning via kernel ridge regression, and then it just forms the statistical model from before. So if you want to know, then calculate an out of sample molecular property, all you need to do is provide it with its Camry value, and it corrects it to give you the Ferrari level. So there's a lot more going into it, but I think that's all we need to know. So I'll just show this picture. Now our Camry level is our red B3 lip there. So just so we don't think, oh, red must be a red Ferrari, I've just included a red Camry down there, and a black Ferrari. So these are out of sample energies calculated using this method. So here's our Camry level, the B3 lip, and it gets the energies wrong just about all of the time. Sometimes it does kind of okay compared to the Ferrari level. Other times it's just really bad. So and the blue here is the corrected result. So as you can see, after training the training our model on 1,000 molecules on the expected difference between the Camry and the Ferrari level of theory, the machine learning result basically gets there within one kcal per mole, which two chemists is considered considered a chemical accuracy. So here, on this point, on number 8, it does really well. So the Camry does really poorly, but the machine learning actually corrects that energy. Over here on some, it actually performs worse, but overall, I think they might be on to something here. So just to wrap that up, so So highly accurate quantum chemistry calculations can be very, very expensive. So they can take weeks on a supercomputer. So they, just as a brief note, they also have really long and dumb acronyms. So that methane surface I talked about before was, they use AEMRCIF12 parentheses Q CVQ ZF12, whatever that is. But we don't have to do that. So if we have our training set of those accurate energies, we can accurately predict those properties using a machine learning correction to our sort of baseline cheap level of theory, so our Camry. And I think just overall, machine learning techniques are becoming more and more prominent in computational chemistry. I've only really just scratched the surface here, and I think as the years go on, they'll become much more common, and they'll probably be just used routinely all the time. Which takes me to, well, I hope. Oops, I had a picture here that disappears, but well, never mind. But it was just a computer keyboard with a chemistry button on it, and if we do really well with our machine learning, maybe we'll put people like me out of a job. So we just do our computational chemistry just by mashing that chemistry button on the keyboard. But on a lighter note, I just found this picture when I was putting together this talk. It's some molecule skiing with a sort of pressure valve as a head. I thought I'd just leave the talk with this picture here. And so I would like to thank you all for coming tonight and just hearing about some computational chemistry. Thanks. Yeah.
Of course, Ashley isn't Jordan. Jordan's not getting away this easily because now he gets asked questions. I have a question for you, Jordan.
Yep.
Those methods, were they methods that you're actually implementing yourself, or are you just giving us an overview at this stage?
As I said in my disclaimer, I haven't I haven't used any of these methods myself. So I'm just reporting some work that's been.
That's all right. I'll hold off on the friendly advice then.
Yep. So with the potential energy surfaces, I use a different method, which could be seen as a sort of distant cousin from machine learning. But I calculate the potential energy surface in a bit of a different way.
Yep. So my question is, have you ever come across someone who's used, for example, different basis functions or transforms and things in neural networks and had better results, like if you use a quantum-inspired one rather than a simple?
That's a good question. From what I could tell in looking through the literature, I think they all just use a sigmoid functions. I think they seem to work the best for what they're trying to do. I don't think they've probably tried some different ones, but they all just fall back on the good old sigmoid function.
One over there.
Quite quickly, if your neural net came out as an answer, would you know it and it was wrong answer? Would you know, or would you have to do some other method of checking it?
So I suppose if it gave you one wrong answer, you might not know. If it's giving you heaps of wrong answers, your simulation might do something really weird and unphysical, or something that just goes against all the chemical intuition. So we have our methods, but as chemists we also, if our simulations do something and it goes against everything that we know about chemistry, then we'll probably say, oh, our underlying method's wrong.
What's it like using Fortran?
That wasn't a very nice question. Well, you learn to live with it, really. Like living with a really annoying roommate. You just learn to deal with it. But you also get used to it after a while. So yeah. So it isn't the end of the world.
So you mentioned that the neural net, or the second method, used the approximation from the error difference between the Ferrari and Camry.
Yep.
But you mentioned to calculate the Ferrari was a really difficult and expensive process.
Yep.
So they obviously need to do it a few times before they can actually make use and leverage the machine learning.
Yep.
Is there any way that they can cut that down further that you're aware of? Because if it's so expensive, it seems prohibitive initially.
So as far as I know, I don't think you can you can get out of actually not doing any of those for Ferrari calculations for your training set. But there's outside of machine learning, there's other groups looking at ways of how to better scale these types of algorithms. So if they have some breakthrough, then maybe we won't actually need the machine learning. We can just do the Ferrari calculation. But until that happens, you do need to sort of do some of these calculations for the training set.
All right, I'm sure there's more questions for Jordan, and this is why we have the 5-minute break. I can see food. Stay away, it's mine. I'm getting it first. So 5 minutes, and then our next speaker. See you soon.
Thank you very much for the presentation.